We present learning adaptive safety in multi-agent systems. We consider the problem of learning a safe controller in multi-agent systems where the safe set of states is delimited by a control barrier function h. The CBF enforces safety through the following CBF constraints. However, apart from the design of the CBF itself, the class K function plays a significant role in the emergent behavior. Multi-agent systems pose unique challenges for the design of CBF constraints. First, all the agent policy may be unknown, introducing partial observability and hindering the safety guarantee. Second, prior data of interaction may be unavailable or incomplete, making offline optimization impossible and motivating the need for an online approach. Finally, CBF pointwise optimization does not capture long-term objectives as shown in the simulation. Against non-cooperative agent, a low CBF coefficient helps in evading maneuver and reaching the target. However, under the same configuration with cooperative agents, a low CBF coefficient cannot reach the target within the time limit, while a high CBF coefficient does. This shows the need of training adaptation to account for delayed events. Instead of a vanilla CBF, we adopt an adaptive formulation. Introducing state-dependent coefficient allows us to switch between conservative and aggressive modes based on the context. We integrate this into a trainable framework called adaptive safe reinforcement learning. Here the agent has a hierarchical structure. At high level, it's composed by a representation model which encodes past observation into a latent vector, a policy which proposes candidate actions, and an adaptive safety module which selects the CBF coefficient. At low level, the CBF condition enforces safety with action and coefficient from the high-level component. We train this approach with constrained model-free reinforcement learning directly interacting with the other agents. In practice, we model safety as a chance constraint and solve the constraint problem by Lagrangian relaxation. We invite to read the paper for further details. In the experiment, we consider two multi-agent environments. Compared with safe reinforcement learning baselines, our approach, depicted in blue, shows faster convergence to near-optimal solution, and most importantly, it keeps the violation rate around the desired limit thanks to the integration of adaptive safety. In the second experiment, we study the impact of the adaptive safety component in isolation by fixing the policy with a built-in controller and only training the adaptive safety module. Compared with control-theoretic approaches, including standard and adaptive CBF, we show a significant improvement in terms of success in green, collision in red, and episodic length in blue. This is thanks to the trained adaptation. Finally, we studied adaptation and generalization to out-of-distribution conditions, including number of agents, increasing velocity of the opponents, and previously unseen planners. Here we show a selection of demonstrative videos from one of the trained agents, and for more detailed statistics we invite to refer to the paper.